Hello, welcome to your first vodcast of Biology 12. You'll see these vodcasts periodically throughout the semester, and the purpose of these vodcasts are so that you are able to access the learning at home in order for us to work through problems and advance these concepts in class. So our first vodcast is a chemistry review. In order for us to understand human biology and have a language that we can all discuss the human body, we need to have a basic understanding of chemistry. And so we're going to review some of that before tackling the biochemistry. Now, what I suggest is that you write notes on the things that you do not know, as this is all material that you'll be required to have some understanding of. So we're first going to start to look at the structure of an atom and break down the component parts of an atom. So what I want to draw your attention to in this diagram shown here is this cluster. First off, is this cluster here. Let's get this, it's moving. This cluster here in the center of this diagram. So you can see that there's two different colors of circles in this cluster, and I'm hoping that some of you might be able to remember the name of this center of an atom. It is the nucleus, and inside the nucleus we find two of the subatomic particles, and in the next slide we'll go over what those subatomic particles are. So additionally, on the outside of this nucleus is this structure here. You can see that there seems to be these little kind of elliptical shape structures that seem to be kind of rotating around this nucleus. And so you can see there's little yellow dots on that also. And in the next slide we will also discuss what these refer to. So this is a simplified diagram of what you saw on the previous page. You can still see here there's still a cluster of subatomic particles within its nucleus, and rotating around in shells on the outside of the nucleus is that third type of subatomic particle. Before we define and name the three types of subatomic particles, let's define what an atom is. So an atom is the smallest part of an element that displays properties of that element. So what that means is if you begin to change the number of particles within an atom, you will be changing its properties of that atom. So here is what we need to discuss. So there are three subatomic particles. Atomic particles, and these are the three different colors of circles that you see inside in this diagram here. So our first type, the ones in red, these are our protons. So protons, that needs to be an O. Our next type, still within the nucleus, these are our neutrons. And so these are our two types of subatomic particles that are in the nucleus. So these are the ones that take up most of the space within an atom. Now our third type of subatomic particle, these are our electrons. And so these are the ones that you find rotating in shells. So these ones are outside the nucleus. Outside nucleus. Now, not only in terms of their placement of where they're found, that is important, but additionally also the charges that you find on each of these subatomic particles. So our protons, they are positively charged. And our neutrons are neutral. So they do not have a charge. So I just put a little zero with a line through it. They do not have a charge. So the overall charge of the nucleus then is always positive. However, when looking at the whole entire atom, if we look at the electrons, our electrons are negatively charged. So the electrons and the protons is what makes the overall charge of an atom. And so for an atom, the number of protons will be equal to the number of electrons, so that in an atom, your overall charge is 0. So on the atom, the number of protons is always equal to the number of electrons. However, atoms do have the ability to gain or lose electrons, and when they do that, they form ions. And ions are usually signified by showing you the charge in which the ion contains. So here you can see all these superscripts beside these ions that are written down, because what that means is that the protons and electrons are not balanced any longer. Depending on the charge, you might have more protons, and hence you have a positive charge, or you might have more electrons, and hence you would have a negative charge. So here's an example. Here we have the sodium atom, You can see that these are both listed as atoms, the sodium and chlorine. This sodium here has this one valence electron. Now it wants to be stable, and so it wants to get rid of that one valence electron, so it has a full outermost shell, and full in this case would mean 8. And so therefore it wants to transfer that one electron to another atom, and it just so happens that this chlorine only has 7 valence electrons in its outermost shell. So it's going to be happy to accept that one electron to make it 8. When there is this transfer of electrons, they now become ions, as you see on this lower diagram here. So here was that one valence electron that used to be over at the sodium, and now the chlorine has taken it up. Hence, the chlorine has taken on an electron. Electrons are negative, so it becomes negatively charged. The sodium has lost the electron, and therefore it has become positively charged. And in doing so, this sodium and chlorine is actually bonded together. Now, this is the example we're going to use to talk about ionic bonds. So there are 3 types of bonds that we're going to discuss. The first one I've just mentioned. So the first one is the ionic bond, and this is when you see a transfer of electrons from a positive ion, that was the sodium, to a negative ion, that was the chlorine. So this is where it involves a transfer. So how we can also look at this is, if you remember your periodic table, and I'm just going to draw a quick sketch of a periodic table, and then we had this staircase here. So here's a periodic table. Now the positive ions tend to be found on the left side of the periodic table. Your negative ions tend to be found on your right side of your periodic table. These can be also called your nonmetals. I hope you don't hear the squeaking of my pen. And these positive ions on this side tend to be your metals. So an ionic bond usually occurs between a metal and a nonmetal, or a positive ion and a negative ion. The second type of bonding is a covalent bond. So these are where atoms share electrons. So this occurs between 2 nonmetals. Now remember from our last slide, these were where you find the nonmetals or the negative ions. And so this occurs between 2 nonmetals, and it's a sharing of electrons. So here's some examples of covalent bonding. Here we have 2 hydrogens. These are both nonmetals, and they are showing that there's a sharing of 2 electrons here. And so we call this a single covalent bond. So it's a sharing of 2 electrons. So there are a few different structures in which we tend to show molecules or compounds. This one here, this is our electron model. These are taken from the Bohr diagrams. If you remember back to your Chemistry 9 and Chemistry 10, you discussed Bohr models. We also have structural formulas. So these are showing how the atoms are bonded to each other. Note here, this solid line that you see between these 2 hydrogen atoms represents a single covalent bond. So it represents the sharing of 2 electrons. And here's the molecular formula just to show you how many atoms are actually involved in this type of bond. So the second type to show here, this is a double covalent bond. So with a double covalent bond, you're going to see 2 lines, because this is showing 4 electrons being shared. So here are your 4 electrons that are being shared in an oxygen molecule. So those 2 lines, each line represents 2 electrons being shared, and so this means that there are 4 electrons being shared in this oxygen molecule. Now we can also have triple bonds, which would look like 3 lines. Here's an example of a molecule that triple bonds with each other, and so nitrogen gas will have a triple bond. Okay, so there are 2 subcategories of covalent bonds. The first one I want to talk about is the nonpolar covalent bond. So as you can see by the definition here, this is where electrons are shared fairly equally between atoms. So here's some examples over on the right-hand side. Here we have, again, hydrogen gas, the hydrogen molecule. You can see that these 2 electrons here, they will rotate around this hydrogen. and then one will rotate around this hydrogen. And so they spend equal amounts of time around all of the atoms within the molecule or within the compound. And so they just continue to rotate around each of those hydrogen molecules. Here's another example. Here's methane. So methane will again equally share these electrons around each of the molecules. And so they are shared fairly equally, and therefore they are called nonpolar covalent bonds. Another key is the symmetry of them. If you look at their structural formula, they are symmetrical. And so symmetrical compounds or molecules tend to form nonpolar covalent bonds. The second subcategory of a covalent bond is a polar covalent bond. So now this is the unequal sharing of electrons. So the unequal sharing of electrons, the most common one we're going to come back to over and over again is water. And here's a diagram for water here. As you remember, the molecular formula for water is H2O. Here is this one oxygen here, and here are the two hydrogens. You can see that they are not symmetrical. If I was to draw this out with its covalent bonds there, they are not symmetrical. There is actually, if you look at this degree difference, it's not 90-degree difference or 180-degree difference. So what this does, this creates a dipole, which means that this oxygen here, this holds onto those electrons more often than these two hydrogens do. So I like to call this oxygen, it's a big pig. It hogs the electrons more often than the hydrogens are able to hold on to those electrons. So what that means, it creates a slightly negative end and a slightly positive end. So these little funny shapes here mean that we have a negative dipole and a positive dipole. So we would call this one, this would be your negative dipole, and this here would be your positive dipole. So it just means a slightly negative end and a slightly positive end. Again, because this oxygen is more electronegative, it's what I call the big pig. It holds onto those electrons more often than these hydrogens do here. Okay, so here's our third type of bond. This is a hydrogen bond. Now it's important not to mix up hydrogen bonds with covalent bonds, because here's the issue. Here is our water molecule. As we know, the oxygen is covalently bonded to two hydrogens. Because this oxygen is a big pig, it creates a slightly negative end and a slightly positive end, which means it creates a dipole. Okay, so in order for you to have a hydrogen bond, you need to have a compound that contains a covalent bond with usually oxygen, nitrogen, or fluorine in it. We're always going to be using the example of water because we're going to start to talk about our biological systems and how important water is. So let's look at this diagram down below. Here we have water molecules. So these red ones, as you can see, they're larger. They must be the oxygen. Here are these white ones because there's two of them. These have to be your hydrogens. And each of these molecules are already showing you the positive end, the slightly positive end, and the slightly negative end. They're showing you the dipoles. Here's your slightly negative, your negative dipole. Here's your positive dipole. Notice your negative dipole is always beside the oxygen because the oxygen holds onto those electrons more often than the hydrogen do. So those are where you get your dipoles from. Now, and just like any other theory that we've ever studied, magnetism, even ionic bonding, opposites attract. So the negatives are always attracted to the positives. So here's the difference. This is showing you covalent bonds. This here is showing you hydrogen bonds. Hydrogen bonds are always represented by dots, and they are always occur between compounds. Not within the compound, because within is the covalent bond. Between compounds is the hydrogen bond. So we're going to come back to hydrogen bond because we are going to discuss water in much more detail. But this is the end of your first vodcast. I hope to become better at this and so that you stop hearing my squeaky pen and I don't talk as much, which you'll probably get used to in my class. Ms. Schuck might be better with these, so good luck.